Okay, so on Friday we looked at the first minimum spanning tree algorithm, which was Kruskal's, which was pretty simple. All you had to do was consider all of the edges in non-decreasing order, and in other words, you had the least weighted edges first, and then you added them to your spanning tree until or unless it would induce a cycle. And in a tree, you don't want a cycle, so you would reject it. And you kept adding them until you had n minus one edges in your tree, which spanned all of the other vertices, the n vertices that you have in the tree. Now, when you go to actually program this, you will have to consider the possibility that you might have a disconnected graph, in which case you would be building a minimum spanning forest. The way that we presented it, we said, okay, well, we'll just assume that the graph is connected, and then we'll go ahead and stop when we've got n minus one edges in our tree. Now, with your programming assignment, of course, you're going to have another stopping condition. When either you've connected all the components together, or the easiest thing is just to wait until you exhaust all edges. And then that's your minimum spanning forest, which is going to be a bunch of disconnected trees. I want to look at another one because the idea is very, very similar to the next algorithm that we're going to look at after this, Dijkstra's algorithm. It's called Prim's algorithm, and it takes a little bit of a different approach, a different strategy. Instead of just considering all edges at, and then in some order, it actually tries to build it out from an initial vertex. So the idea here is that you have to work locally. You start at a vertex, and then you start adding things that are close to it. It's similar to BFS because you work outwards, right? That you visit things that are in the immediate neighborhood, and then the neighborhood of the neighborhoods, and then the neighborhood of the neighborhoods until you've built out the entire tree. But instead of BFS visiting everything, you consider the least weighted edge next. This means that you've actually got three regions. The way that we're going to visualize this algorithm is that you've got tree vertices, fringe vertices, and unseen vertices. Tree vertices are vertices that you've already added to your minimum spanning tree. Fringe vertices are things on the frontier, things that are in the neighborhood of any tree vertex that are immediately connected by it. And so all of these are going to have some sort of weight attached to them. This is what we want to consider next. We're going to consider adding some edge over here. And the way that we're going to do it is we're going to be greedy about it. We're going to consider the least weighted edge next. Well, say that it's this one, right? Say that we add this edge right here. Then that means that we're going to take this vertex right here and we're going to move it over to our tree set, right? That takes, because it's no longer part of the fringe set, it's part of our tree set because we took this edge right here. Now that's going to cause some different effects. First of all, anything that was unseen is now going to be pulled over to the fringe set. And in other words, anything that was in the neighborhood of this vertex is going to be pulled into its into the fringe vertex set. And in addition, anything that potentially, anything that was connected, say that it was connected to this thing over here, maybe it was connected, it's got another edge over here that's connected to this tree, we end up not taking this thing. And ultimately, we'll have to make sure that we don't take this because that might induce a cycle. That you're somehow connected to this edge over here. So if you take this edge right here, then you certainly cannot take this edge over here. So in other words, if we take one edge over here, that means that we eliminate a lot of these edges from this fringe edge set, if you want to call it that. Okay? So let's go ahead and look at it with an actual example, and then we'll write down the pseudocode and analyze it. I'll just pull the example that I've got in my notes here. A, B, C. 7 and 8. And by the way, as I'm writing this, understand that these two algorithms can result in completely different trees. And that is perfectly fine because remember, we're only looking for a minimum spanning tree. There might be several. In fact, there might be exponentially many different spanning trees, all with the same minimal weight. E, F over here, connected here, here, and here. And then just one more. There we go. And we'll put in all these weights here, 8, 9, 8, 15, and 6. All right. So let's go ahead and visualize this. I'll go ahead and, again, you can start arbitrarily because everything is going to eventually have to end up in the minimum spanning tree. So let's just go ahead and start here, right? This ends up being V sub t, where V sub t is going to be the tree vertex set. All right. Let's go ahead and also update our fringe vertex set. Right? What are the vertices that are in the fringe right now? Those are the things that are connected to the tree. So B and D. Right? And their associated weights. And let me go ahead and draw them vertically here. B and D with an associated weight of 5 and 7 respectively. In other words, this is your fringe right here. Okay? This is the first now this is the initialization of the algorithm. Now sorry, go ahead. Oh, 7 B 7 and 5. Okay. Sorry. 7 and 5. Thank you. All right? And then of course I won't bother writing the unseen vertices. That's everything else. C, E, F, and G. They're not on the frontier, right? They're not on the fringe. They're way outside the fringe. So we're not going to consider them until we pull something into the tree, which consequently pulls something into the frontier, right? The fringe. This is our fringe right here. Okay. So we're only considering things that go from the tree vertex set to the fringe vertex set. And what do? We're going to be greedy about it. We're going to take the thing with the minimum weight. For this, let me go ahead and grab my other color here. Right? So we're going to go ahead and take this edge right here. Now that changes the tree set. Right? Originally it was just A, and now we've added D because we've added this. And now this is going to expand. And there's our tree now. And it also changes our fringe vertex set, right? B is still in the fringe. This is gone now. This is out of the fringe because we pulled this into the tree, and now we've got a bigger tree. But now this is my frontier, right? Which pulls a couple of things in. First of all, there's B that's still there, but there's also E and F, right? And in fact, we now are connected to B with another edge right here. So technically, we have B9. We've got you can look at it as either being duplicates, or you can say, depending on the data structure that you use, you can say, well, B is already in there at a weight of 7. But if I happen to have these weights reversed, I would need to kick out the 9 in favor of the minimum one. It's not going to matter much because as we're going to consider these, we'll consider 7 and then, we'll consider B again, but it's already in our tree, so we end up ignoring it. I'll go ahead and go that direction. So I need to add B7, B9, E15, F6, and there is my frontier now, and my fringe vertex set are these 3 now. Okay? So again, I go through and I choose the minimum here. Well, F has the minimum weight here, so F gets added to my tree. And the edge that is associated with that is that one right there. And so now my tree has expanded. It's now this. Right, there's my tree. Again, I'm building out. Not only that, but I've added a couple of more things now. E is connected by 8, and F is connected by, G is connected by 11, right? And those are now in my fringe vertex set. Understand here, though, I've got duplicates. I've got B and E. In fact, now that I can see this edge right here going to E, I found something that connects E at a less weight. So again, you can conceive of that as kicking this out of consideration. But the data structure we're eventually going to use, a heap, we don't need to worry about that. And I'll show you why here in a second. Okay? All right, so that's my tree now. Which one do I consider next? Go through and I choose the minimum, which is, oh, sorry, I already chose this one, right? And so that's gone. So what's the next minimum? It should be B. Remember, we've still got this one up here, right? And that's not in my tree, so I go ahead and add it, right? And now that's out of there. So let me go ahead and highlight that now. And my tree has expanded yet again. There's my tree now, okay? At this point, I've added a few things. Look, by adding B here, then the fringe vertex set, I can go to C at a weight of 8, and then I can go to E at a weight of 7. Right? Again, E now has multiplicity 3. It's in here 3 times. We're not going to end up adding it 3 times. We're going to end up adding it once and then rejecting the rest. Okay? What do I consider next then? Did I get everything? Yeah, I got everything. Right, now what do I add? What's the minimum here? The one of the ones that I just added, right? This one right here, going over to E at a weight of 7. And now my tree has expanded again. There it is. Go ahead and add E up here to the vertex set. By doing that, I look at the neighborhood of E. All 3 of these are already in my fringe vertex set, and so is C and G. But now I can get there at 5 and 9. Right? Okay, so what do I add next? C, right? Because that's the minimum weighted one. So C at a weight of 5, and I end up adding that. And now my tree spans every single vertex except for the last one. How do I end? But before I do that, let's look and ask ourselves, what do we consider next? Technically, C or E, right? But both of those are in my tree already, right? Let's go ahead and say that I'm going to consider this one next, right? Well, I've already added that to my tree. So should I add it again? Nope, I can go ahead and reject it, right? I can see, is this element in my tree vertex set up here? If it is, well, you don't need to add it again. Go ahead and reject that and throw it out. That's why it's okay to have duplicates over here, because ultimately you'll reject all the ones that you don't want. And then the next one that we would consider is E, but again, that's already in our edge sets, or our vertex, or our tree, so we would end up rejecting it. Then what? Then we consider B9, if you want to go in lexicographic order, but that's already in there. And then the last one we would consider is this one right here, adding G off of this one. And now my tree spans the entire graph. Once I've reached all of the edges, by the way, once I've reached that counter, whatever else is still in this data structure that I'm considering over here can be thrown away. I can stop prematurely and say, there's my minimum spanning tree. Just to make sure that we understand what the weight of a spanning tree, minimum spanning tree, it's going to be 5 plus 6 plus 7 plus 7 plus 5 plus 9. What is that? 14, 25, 29? 14, 25, 39. There we go. And good, I got it. I think that there's another minimum spanning tree of equal weight, but go ahead and as practice, run Kruskal's algorithm on it instead. Okay. So here's the question: what kind of data structure would be appropriate to hold these things? I was putting stuff out. I didn't really care what they were put in. When I took them out, what order did I want? With respect to what data structure allow you to going to be order M, where M is the number of edges that you're adding to this thing. Of course, it's going to be even better than that in practice because you don't add all the edges at once. If you added all the edges at once, you're basically doing Kruskal's algorithm then. Throw in all of the edges, take up, then go ahead and add it to your collection. So they're very, very similar. Let's go ahead, but they are different in how they end up building the tree. And of course, they can end up with different minimum spanning trees, although they're equivalent minimum spanning trees. So here's Prim's. Our input is a weighted, undirected graph G. Okay. And initially, and our output will be a minimum spanning tree of G. Okay. Initially, our edge set is going to be an empty set. Just like when we started out with one vertex, and we'll go ahead and initialize that to the first vertex. Again, it doesn't matter. You can go ahead and start on an arbitrary vertex. I'm just going to go ahead and go with the first one, all right? Whatever that might be with your representation. I'm going to also define a fringe edge set, right? And this is going to be, fringe, I don't know why I call it E, but I end up doing vertices. So this could be seen as a fringe vertex / edge set, right? However you want to, conceptualize it. Do you want to maintain both a vertex set and an edge set, or do you want to maintain a mapping between the two so that when you put it into, say, a min heap, you can get the least weighted one according to the edge weight next, right? So for I equals 1 up to n minus 1, we're only going to go n minus 1 iterations here because each iteration, what did we do? We added a vertex, right? So the way that I'm going to present the pseudocode at least. E is going to be the edge that we want to add next. It's going to be the minimum weighted edge in E star. And if you've got multiple minimum weighted edges, you've got 3 edges that are of weight 5, and that's your minimum. Go ahead and break ties arbitrarily. It doesn't matter, okay? U and V, I'll steal some Python kind of stuff here. This is going to be the endpoints of E star, or no, sorry, E, such that U is in VT and V is not. In other words, U is the endpoint in your tree. This is the tree so far, and this is U, and U is connected to V. V is in the fringe, okay? We're going to add V to the vertex set for the trees, right? We're going to add E to E sub t. This is the edge set for your tree, right? And then we're going to update E star. The way that we're going to do that is we're going to add all vertices / edges in the neighborhood of V, right? Because we pulled this fringe vertex, we've pulled it into the tree. Anything that is connected to it is now part of the fringe if it wasn't already, okay? That's 1. And 2, you can remove or ignore, eventually, all edges in n sub V connected to V sub t, right? The algorithm is just when it came up, I forget about it, ignore it, right? That, of course, would change how you're doing your for loop up here. Otherwise, you can go through and you can change, or you can go through your min heap and say, all right, I no longer need this edge because it connects two endpoints of my tree, so we can go ahead and throw it out. That can be quite expensive. If you just ignore it, right, when it comes out, then that's less expensive. Because it's more expensive to go through the entire min heap, find things that you no longer need and kick them out, than it is to simply just wait for them to heapify up, see that you don't need it at the top, and then throw it out. Right? So either or, it doesn't really matter. Okay? At the end of the day, we're going to output our tree, which is going to consist of the tree vertex set and the tree edge set, and that's it. Okay? So if I do use the min heap, and I'm putting all of the edges insertion of an edge into a min heap is going to be what? In the worst case, if I have all edges in the min heap, then what is an insertion operation? It's the number of maximum number of edges, right? If I do this n times, and I kick things out on the fly efficiently, or I just ignore them, then it's at most in total. You're going to end up doing this either n times or m times if you want to, reject all of the edges. And so in total, it's going to be simply just m log m. And if m is considered as your input size, then this is quasi-linear, right? Because it's m times log m. Right? If you ignore the lower order term here, then it's going to be linear in m. Right? And again, I would do this with a min heap. Okay? Because if you get through and change things out that you need, amount of work to find it. If you maintain a dictionary and you can jump right to that node, you'd really have to think about how you're going to handle that with a min heap, right? So that's why I like to present it as, well, don't worry about it. When it bubbles up to the top and you no longer need it because it's connecting two things that are already in your tree, then just throw it away, right? And don't increment I when you do so. Okay. Okay. Again, I like to cover Prim's algorithm because it shows us an idea that we can then adapt for a different problem. The idea that we're going to adapt for this problem is Dijkstra's algorithm. His algorithm works for single source, and it works on both directed and undirected graphs, but I'll go ahead and show it for undirected graphs, or for directed graphs, excuse me. Single source, shortest path. Right? In other words, given, again, undirected, directed, I'll go ahead and we'll go with a directed graph. A directed graph, G equals V comma E, and a start vertex, S, we will output the shortest path from S to all other vertices. Now, the algorithm itself is called single source. S is not necessarily a source. S could be a sink, in which case you would return an empty set that you can't get anywhere, right? It could also be neither. It could be a source, or it could be something that is neither a sink nor a source. But for the purposes of this algorithm, we're calling it a source because that's where we're going to go from. It does not give you, if I go from S to Y, it gives this algorithm is going to give me the shortest path from S to Y, but it's not necessarily going to give me the shortest path from Y to S. If you wanted that, you would have to rerun the algorithm with your initial source vertex as y. So you'd have to run Dijkstra's algorithm multiple times to get all pairs shortest paths, which is something that we're going to talk about with Floyd's algorithm. Okay? So that's the idea, right? It works generally with directed graphs or undirected graphs, and it has a start vertex. Now, the way that this works is very similar to Prim's algorithm, where it maintains tree vertices. It maintains a set. What do I call them? Yeah, it maintains a tree vertices, and it maintains fringe vertices and edges. Right? That's not what I want. Sorry, say again. Oh, you get some choices, right? You do, you have to report the shortest path between every two vertices, and so you could do Dijkstra's algorithm multiple times, or you could do Floyd-Warshall's algorithm multiple times. The only caveat with Floyd-Warshall that we'll take a look at here after this one is that it doesn't work with negatively weighted cycles. I don't know that we put anything like that in the test suites, though. So I think that you'll be able to apply either one of these, just like minimum spanning tree. You could do prims, you could do crucibles, you could do something else if you want to go out and look at other minimum spanning tree algorithms. And there are at least a half a dozen out, right? So yes, this will take this and Floyd-Warshall's will take us up to the end of homework 3, which again is due on Wednesday. Okay, but don't let that stop you from getting started if you haven't already. You can do pretty much 80% of the assignment right now. Right? Okay, so we've got tree vertices and fringe vertices, and what we're going to do is we're going to consider edges on the fringe, and we're going to add the least weighted total edge. Now, this is unlike Prim's, where we're just going to add the one with the least weight by itself. What we're actually going to do is we're going to add the, it might not be the least weight, right? For example, I could have a least weight 1 and a least weight, say this guy over here is 2. We might end up taking this one because to get here, right? To get here, say may cost us 10. To get here, it might cost us 20. Well, would you want a path that gave you 12, or would you want a path that gave you 21? This is the path that we're going to choose next, okay? And so what we're going to do is we're going to consider the summation of weights all the way up to that point to make our next decision. That way, it's going to optimize the single shortest path rather than optimizing a tree itself, okay? So what I'm going to do is I'm going to simulate this on a much larger graph here. In fact, yeah, you know what? I've got it in my notes. I don't have to redraw it. Let's go ahead and use it. And let's go ahead and zoom in if you want. There we go. All right. So I'm going to keep track of several things here. I'm going to keep track of everything that is in the fringe, right? In fact, I'm going to keep track of everything all at once. And then we're going to put n things into a data structure. Again, spoiler alert, it's going to be something like a min heap. We're going to keep track of, and I will do with a pencil here, we're going to initialize everything. And let's see, this is from vertex E, right? So we'll go ahead and start at E, right? S is equal to our start vertex here is going to be E. I'm going to look at every other vertex, and I'm going to keep track of two things. I'm going to keep track of the distance, the minimum distance, and I'm going to keep track of what's called a predecessor vertex, piece of E. Okay? So A, B, C, D, E, F, G, H. Is it all? I, J. There we go. Okay. Well, initially, if I just look at this in isolation, I haven't discovered any fringe vertices yet. So the minimum distance to everywhere, I'm going to go ahead and set that. I'm going to ramp it up all the way to infinity. Because if I actually find a path to another vertex, say a path to B from E, well then any path that is finite is going to be of lesser weight, of lesser distance than infinity. So I'm going to initialize all of these things to infinity, except for E. And I can get to E at a distance of 0, because if you start at E, well, just stay there, right? It's a distance 0. And these are all going to be infinity, 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 right? And then the predecessor vertex is going to be initialized to nothing, right? Nil, nothing, none, whatever you want, whatever placeholder value you've got. Tell us how you got there. I can get to G from E. All right, so on our first iteration, we're going to look at E and we're going to look at its neighborhood. Now remember, this is a directed graph, so we're only looking at outgoing edges, which are going to be B, D, and E, okay? So I update these things. I can get to B from E at a weight of what? I can go from E, because this is where I'm currently considering it. I can get there at a weight of 5. And my predecessor of how you got there is, well, I came directly from E. Likewise, D is going to end up being updated to a distance of 5 with a predecessor vertex of E. And G is going to end up getting updated to 20. All right? That's the update with respect to E's neighborhood here. Okay? Now what I do, that was the initialization. What I'm going to do is I'm going to go through this list and I'm going to start getting rid of things. Well, sorry, one thing that I would have gotten rid of immediately is E, right? So let me go ahead and put that over here. E with a distance of 0 and no predecessor vertex, that gets kicked out of consideration. Once, in fact, I kicked it out and then I looked at its neighborhood and I updated everything in here. That's the order. Okay? So, what's the next thing that I check? Or what's the next thing that gets kicked out of here because it has the minimum weight? It's going to be B or D. So let's go into lexicographic order. E, weight of 5, predecessor E at the time that I kicked it out. There we go. I will go ahead and keep track of that by highlighting this edge over here. Right? And now I look at its neighborhood. It only has one outgoing edge. And so I look at A. I can get to A at some distance. What is that distance? I can get there from 7, but remember it's single source. I can actually get there from E at a distance of 5 plus 7. So 12. Is 12 better than what I've found so far? Yeah, anything's better than infinite. So I will update this to 12, because this is capturing the distance from E, not just the local edge information like you would in Prim's algorithm. Okay? So this gets updated, and the predecessor vertex here is B. How did I get to A at a cost of 12? Well, you got to B. Well, how did I get to B? You went from E. Right? So you're going to, these are all your breadcrumbs. This is how you're going to be able to reproduce this path. The next thing I consider is, well, the minimum value here is going to be D at a distance of 5, predecessor vertex E. So this gets kicked out. I solidify this edge right here. Okay. And now I look at its neighborhood, which is quite large, right? I could go to B, I could go to A, C, F, and G. Do I even consider B? Nope. Why? It's already in there, right? So no. Yeah. No. Let's see. So what else do I consider A? I could get to A at a cost of 5 because I'm currently considering D. I got to D with a cost of 5. I could get to A with a cost of 5. So is that better than what I've found so far? Yeah. 10 is better than 12 if you're trying to minimize things. So I update this to 10. This predecessor vertex has been changed to D. C. I can get to C at a cost of 5 plus 20. What's that going to be? 25 with a predecessor of D. Right? That gets improved because it was infinite before. F is going to be a cost of 25 with a predecessor of D. There we go. And finally, G gets updated to a cost of 5 plus 10. 15 is better than 20. And I update my predecessor vertex here to D. Okay? I just want to make sure I'm not drawing myself down a bad path here. Okay, we're good. And there. Okay? The next thing I consider is A, because it has the least weight here. So A, 10, and its predecessor vertex D is copied over. It's now out of consideration. I have solidified, I came from D, so I've solidified this edge right here. And I look at its neighborhood, but guess what? A is a sink. So there is nothing to consider, there's no update here. Okay? Next thing I add is G at a cost of 15 with a predecessor vertex of D. And I look at its neighborhood. Well, most of those are incoming edges. Its neighborhood is only F and I. Now F, I can get to G from D at a cost of 15, with a further cost of 10 to get to F. So 25, do I update? Not unless you're breaking ties by the last one that you found or something, right? I found a path that was just as good. Well, just as good is not better, so we won't update it. Right? But I certainly have found a better path. I can get to G at a cost of 15. I can go to I at a cost of 5. So it's going to be 20 with a predecessor vertex of G. Okay. And by the way, I solidified this edge right here. Is that right? It came from D? Yep. Good. Again, I want to make sure. Yep. All right. Kicked G out already. What's the next thing I consider? Well, now it's I, because I can get there at a cost of 20. Predecessor vertex of G. I's neighborhood, I can get back to G, but so what, right? You can get there, but I would make the computation, right? I can get to I at a cost of 20, and I can get back to G at a cost of 15, so for a cost of 35. Well, again, that's not better than what I've already found. 15 is better than 35. But you wouldn't even make that determination there, right? Because it's already in your tree. So when I add, oh, by the way, I added I, so this one right here. What else is in I's neighborhood? F. I can get to F at a cost of 20 to get to I, plus 5 to get to F. Well, I found yet another path of length 25, of weight 25 that I could get to F, so I don't end up updating that at all. Next iteration, I'll go ahead and go lexicographic order here, 25 and D, this guy right here. Kick this out. So C from D, oops. And now I look at C's neighborhood, but it's only connected to A, which is already part of my tree over here, so no updates again. F now gets updated, or it gets kicked out, with a predecessor vertex of D. So going from F from D, there we go. And I look at its neighborhood, and I can see C, and that's it, but C is already over here, and we're good. What do I do now? H gets kicked out with an infinite distance and no predecessor vertex. J gets kicked out with an infinite distance and no predecessor vertex. Why? Is there a way to get to H from E? Look at H. What is that called? That's a source. Can you get to it at all? Never. Can you get to J? Well, you can only get to J from H. Well, you can't get to H. So these two are blocked off from E. There's no way to get to them. Okay? And your programming assignment, your programming is undirected. So unless you've got a disconnected graph, you wouldn't report those. Right? But those eventually get out of your data structure, and this is what you're left with here. So question, without looking at it, can I reproduce that graph? Right? Can I reproduce that tree? Suppose that I'm interested in getting to, I don't know, how do you get to I? So from E, how do you get to I? Right? And at what cost? Right? Well, first of all, if I go to I, there's going to be a cost of 20. Right? So the cost is going to be 20 because that's right here. How do I get to I? Well, the predecessor to get to I is going to be G. So you must necessarily come from G. The predecessor, if I've got I here, what's my predecessor? What came before me? Well, according to this is G. Now the question has become, well, how do I get from E to G? Well, you go over here and you look at G, and you say, well, you first go to, you came from D. Right? Now the question becomes, how do I go from E to D? Well, apparently you just get there by going directly there. And there is the reconstructed minimum path from E to I by looking at all the predecessors over here. Let's verify that. E to D has a cost of 5, right there. D to G is going to be a cost of 10. And G to I is going to be a cost of 5. That certainly matches our computed minimum cost there. Okay? And that's Dijkstra's algorithm. You'd have to, of course, rerun it if you wanted it with all pairs, but that's simple enough. Once you've got it working for one vertex, then you can have it working for any other vertex. Okay? So let's go ahead and map out what Dijkstra's is doing. So our input, this is going to be map out as in, like, let's write our pseudocode. Our input is going to be a weighted, directed, undirected graph, doesn't matter. G equals V comma E. And a source vertex that I will label, again, it's not necessarily a source, but we're going to call it a source because it's for Dijkstra's algorithm, it's the one that we're emanating from. And our output is going to be basically a table, the minimum weighted path from S to all other vertices in the form of the weight plus a predecessor vertex. And these will be labeled as the weight of V and the predecessor of V. Okay? Or you know what? I'm going to call this D, that distance. Okay? Because that's what I do in the algorithm here. So, hint, what kind of data structure do you want to use here? What kind of data structure can you put stuff in, take stuff out, so that you are always getting the minimum each time? A queue, min heap, right? Or min priority queue if you want. That's why I'm labeling it queue. So initialize what we're going to do is for each vertex v in the vertex set other than S, we're going to go ahead and set the distance to infinite. And if you were doing this in Python, what is a value that is greater than all other values but that's still comparable? I'm asking you because I don't know. Can you use inf?
I think there's a
Math.max? Inf? Okay, INF. Math.inf, so you're going to have to bring in the math library there. And cross your fingers and make sure that it's comparable, because if I've got x is equal to 10, is x less than math.inf? I don't know. Right? You're going to have to test those things out. Or another thing that you could do instead of inf is that you could go through and add up all of the weights and get the very, very maximum value. That's going to be finite, and any path is going to be less than that, less than or equal to that. Right? So that's another trick that you can use. And then our predecessor vertex here is simply going to be, I don't know, phi. Right? And then we're going to put it into our queue. NQ V with D sub V. There we go. So we're putting everything into the priority queue so that we can pull things out. For our source vertex, of course, the distance is going to be 0, because if you're already there, then stay there. We are going to initialize this to none. There is no predecessor, because if you're already at S, then stay there. Our tree vertex set is going to initially be the empty set. And then we're going to go into our main loop here. Right? And let me go ahead and go over, because I want more room. Okay? So this is the initialization. This is the initialization of all the vertices. This is the initialization of our source vertex. Right? And we did end up, did I end up not in Q? Okay, so sorry. Q.NQ S and D sub S, so that it works on the first iteration over here. Okay? So for I running from 1 up to n, in other words, for just n iterations here, we're going to dequeue the next available thing. We're going to put it into our tree set. Oops, V sub t union. Did I call it U? Yeah, I called it U. Right. And then what we need to do is we need to go through its neighborhood, and we need to look at everything that's still in the queue and update its priority. Right? So for each, call it V, in the neighborhood of U, without all the tree vertices, we'll go ahead and do the following. If the distance of U plus the weight of going from U to V, is less than D sub V, then we need to do something here. Now understand what this is. In fact, I'll annotate it right here. This is the minimum distance found so far from S to U, plus the weight of the edge U to V. Right? So this is how you got here. This is the weight, the distance, or the weight that it took for you to get to U. Going from U to V would cost you just the cost of the weight of that edge. And this is the minimum distance so far, right? This is the minimum, make sure, U, V, and V. And this is the minimum distance found so far to V, right? So again, it's S, then you get through by going some path over to U, and then from U directly to V. Maybe there was some other path that you got there, represented by D sub V. So which one is better? Is the sum of these two paths better than the sum than what you found so far? Is it less? If so, then you need to update everything. If this is better than what you found so far, then get rid of that. You need to update d sub v to be this lesser weight here, the weight that it takes you to get to u plus the weight of the edge from u to v. Then you need to update the predecessor vertex to be, well, how did you get there? I got there from u. Right? How did you get to v? The predecessor here is u. And then you need to update the priority. Q dot decrease priority to of v d sub v. All right? Now, how can you do something? This might be the first time you've seen a decrease priority in a priority queue or a min heap. Let's just think about that for a second. How could you do that? We'll assume we'll give it the benefit of the doubt that you've got the node in your heap, right? It might be at the top, it might be at the bottom, it doesn't matter. It's somewhere in the heap. Decreasing the priority. Will that necessarily put it, do we need to shove it down, or do we need to maybe shove it up? What do we need to do? Let's think about it. Let's draw a heap. 5, 10, 15, 20, 25, 30, 35, 50, 60. Here's a min heap, right? Min priority queue. Let's say that we had access here to 30 and we need to decrease the priority. Say that it got decreased to, 7. Is this a heap, a min heap? Nope. So where does it need to be? Does it need to be higher or does it need to be lower? Remember, it's a min heap. The minimum thing is at the top. So it's out of sorts with its parent. Okay. What do we need to do then? Or what can we do? Swap it with its parent. Right? Decreasing the priority will only ever let it go up. Right? So when we looked at heaps, remember, if we push things down, and if we ended up pushing this down further somehow, right, we might end up with an issue where it's no longer full. But if we're only ever decreasing the priority and moving things up, well, then we're okay, right? What if I decrease the priority to 2? Well, then I would end up swapping it with the root at which point I stop. So assuming that you can get to that node, you can very easily decrease the priority in order log n, right? That's unfortunately, I think that's a big assumption that is not altogether obvious, especially when this stuff is presented in a CS3 course. But this is order log n. Lovington is the book that was used in this course for a long time. There's also CLRS, and neither one of them goes into the details of how is this possible, right? So the best answer that I could come up with is here's how you do it, okay? So you map a vertex. Looking at the neighborhood. You map it to that node, or that vertex, or an index in your. That's how you get there. So you're not just going to have, if you want to do this, you're not just going to keep track of the array. If you just have the array, if you use another data structure, like say a map, to map a particular element to its priority in the priority queue, then you can go ahead and decrease the priority if it's an array-based implementation. So the takeaway here is that you can do this in order log n time. Okay? And that's it. At the end, we output d sub v and p sub v for each vertex. Given that, you'll be able to reproduce the tree, you'd be able to reproduce the path, and of course you've got the weight as well. Okay? So you're doing this order n, you're doing this order, this one is going to be order m, because you are doing that for every single neighborhood. So for each vertex, you're looking at the entire neighborhood. Well, eventually you'll visit every single edge. This is, of course, you can look at that, look at it from the perspective of, you can actually flatten this out a little bit if you want to, but otherwise it's order n. At the very most, it's going to be order m n log m, or whatever, right? Okay? All right. All right, that's Floyd's algorithm is a little bit different. Well, in fact, it's called, the full name is Floyd-Warshall. So at this point, does that ring a bell? Warshall's algorithm from 235. What was Warshall's algorithm used to do, to compute? Anybody remember? Well, if I can go from A to B, and I can go from B to C, then to make it transitive, I would need to add A to C. Right? Warshall's algorithm was used to do that. Right? Maybe did you have to program it? Does that ring a bell now? You didn't have to program it? No? Yes? Okay. Well, maybe you're not, whatever. The basic idea is that if you are at vertex v sub I, right? Well, what if you could get to v sub j? Or what if you could go from v sub I to v sub k, and then from v sub k, you could get to v sub j. Right? The question here is, can you do it circuitously through this intermediary here? And if so, well, then then you have to be able to get to from I to j. Floyd-Warshall's algorithm is a little bit different because we're not just looking at a transitive closure. We're looking at distances. Okay? Let me get my picture. So suppose that I want to go from v sub I to v sub j. Right? Now, you might be able to get there directly from a single edge. It might take you 2 edges, might take you 3 edges, it doesn't matter. Suppose that we're jumped into the middle of the algorithm here. And suppose that we've got a distance here, I, j, right? And this is the minimum distance from v sub I to v sub j. Right? Now, consider the kth vertex, v sub k. What if I could go from v sub I at a distance of to v sub k at a distance of d sub ik, and then from k I can get there again. It could be a single vertex, it could be an entire path at a distance of k to j. Right? Which one is better? It's kind of like what we just did with Dijkstra's, except it was an entire path and an edge versus some other path that got you there. Right? So if d sub I k plus d sub k j is less than what you found so far, then we found a better path. Better as in shorter or less weighted path. Okay? Well, okay, for each intermediate vertex, v sub k, all I need to do is ask the same question over and over again for all pairs. For each pair, vi, vj, I ask this question. Can you get there through k at a better distance? If so, update that. If not, then you didn't find a better path, leave it alone. V sub k is not a better intermediary vertex. Right? This suggests a very, very easy 3-loop structure algorithm. Right? Let's go ahead and be a little bit more formal about it. This is Floyd-Warshall. Now, the way that we're going to work this one is we're going to assume that it's that the input is a matrix. Our input will be a weighted adjacency matrix representing a directed graph. All right. And by the way, it will work just as well with an undirected graph. It's just that that matrix is going to be symmetric. Okay. And then it's the shortest distance. We're going to output a shortest distance matrix plus I want to call it a successor matrix. And we'll talk about that in a moment here. Except for, before we move on, what's the successor? What is a predecessor? The thing that came before me. What is a successor? It's the antonym. It means the thing that came after me. So we're just going to work in the opposite direction here. Okay? So our distance matrix is just simply going to be an n by n matrix. And it's going to be initialized to the weight or infinity. So for I, j running from 1 up to n, d sub I, j, uppercase, lowercase, whatever, is going to be the weight of going from v sub I to v sub j. In other words, all of the edges, right? This is I did say that the input is represented as an adjacency matrix. This is me setting up that adjacency matrix. Infinite if no such edge, right? And I guess you could say that the input is the adjacency matrix because usually it's 0 to indicate no edge. We're going to want to say that it's infinite because it's no longer going to represent an adjacency matrix. It's going to represent a connectivity matrix. That you can go from I to j at a cost of this thing, but not necessarily by one edge. It's by some path. Okay? And then I will set a successor matrix, S of ij, to be j. All right? For all edges, v sub I, v sub j, and phi otherwise. All right, that's my placeholder that I'm going to use for that's not an edge. Okay, there is no successor. Now, all I need to do is write out these 3 loops right here. Right? So for each intermediary vertex, k, running from 1 up to n, for each pair, I, running from 1 up to n, and j, running 1 up to n, all we're going to do is compute d sub ij as the minimum of d sub ij, in other words, you've already found the minimum path, or d sub I going to k plus d sub k going to j. Okay? And that updates the distance here. So as a note here, if d sub ij is updated, update s of ij to be s of ij. Well, how did you get there? So if we update it, then we're updating it to this thing. Otherwise, it was the original distance. Let's look at our picture again. Right? So we're updating it by going from here to here and from here to here. So what's my successor? My question is, how do I get from v sub I to v sub j? Well, how do I start on this path? I need the successor of v to I, but it's no longer the successor of going v to I to vj through this path right here. It's vi to vj through this path up here. So in other words, I'm changing my question. It's no longer how do I get from vi to vj, it's how do I get from vi to its intermediate vk. And that's already in my successor matrix. As the entry, how do I go from I to k? Whatever was stored there gets updated. Right? And that's the end of my for loop. Again, there would be an if statement in here if you want to be more formal. And we'll output the distance matrix and the successor matrix at the end. Okay? So this is quite tedious because even for a small graph of, let's see, I've got I've got 5 vertices here. I've got 5 vertices. That's a 5 by 5 graph. How many times is this going to run? Well, 5 by 5, 25. By another 5, that's going to be 125. I'm not going to do that. Right? I let a computer do that for me if you want to verify it. But I will jump somewhere in the middle here. Let's see what's... let me go ahead and draw the graph so that we have it. A going to B going to E to going back to D at a cost of 3. Oops, 4. Yeah, fine. I'll just transpose them. 8. I will run some of the interesting iterations on this. So one of the first, the interesting iteration would be the first one. So what is our initial distance matrix? So I'm going to go ahead and go with A, B, C, D, and E in that order. Again, ordering doesn't really matter as long as you're consistent about it. So going from A to A, well, that's a distance of 0. In fact, going from anything to itself is going to be a distance of 0. So that's kind of, that looks like a traditional adjacency matrix, right? I can go from A to B at a cost of 1. I can go from A to C at a cost of 2. Can I go from A to E or D with a single vertex or with a single edge? Nope. So that's when those get initialized to infinity. All right, B, I can go to E at a cost of 2. I can go to D at a cost of 8. But can I go to C or A? Nope. So infinity, infinity. C, I can go to D at a cost of, and I didn't write it down, it was 5. So C to D at a cost of 5, but otherwise I can't go anywhere. Right. D, I can go to B at a cost of 4. Oops, 4. But I can't go anywhere else. And E, I can go to D at a cost of 3, but everywhere else is infinite. Okay? Now, the first iteration, I don't think that it ends up with any changes. Now, why would we not end up with any changes in the first iteration? The first iteration is A as your intermediary. Can I go from anything in this graph to A and then from A go to somewhere else? Well, from A to going to somewhere else, B and C, that's true. But can I get to A? Nope, because it's a source. So the first iteration would result in the exact same matrix here. You would not make any updates. Okay? But on the second iteration, I'm looking at B as my intermediary. A to E. Before, it was infinite. What's it going to be now? I can go from A to B at a cost of 1. And then I can go from B to E at a cost of 2. For a total cost of 3, is that better than infinite? Yep, so this gets updated to 3. And my successor matrix also gets updated. All right? Is there anything else? I can go from D through B over to E. Is that better? 4 plus 2, that's 6. Well, is that better than, what was it, D to E? Infinite? Yep. That gets updated. Anything that you've got B as an intermediary here is going to get updated. I can go to A to B and then on to, I don't know, I guess is that it? Oh, D. A to B to D at a cost of 9. So A to D, that gets updated to 9 as well. Right? And a bunch of others. Okay? I do have 2 examples with the full matrix output from the program that I wrote. So if you want a good test case to make sure that all of your stuff is working, it shows every single iteration of this algorithm here. Fast forward. Right? Here's the final matrix. 0, 1, 2, 6, and 3. In other words, non-zeros are everywhere right here. How do you interpret that? From A, I can get to anything else. Then infinite, 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 infinite. What's the interpretation on this column? Can I get to A from anywhere? Nope, because it's a source. So 0, 9, 4, 7. Infinite, 0, infinite, infinite. How do you interpret that? I can get to C from A or C by just staying there. So in other words, C, the only place that I can get to C here is from A. Right? That's the interpretation. 5, 5, 0, 3, 2, 11, 6, and 0. There. Now, the successor matrix would look something like this. Nothing, B, C, B, B. Nothing, nothing, nothing. D, B, D, and then nothing, nothing, nothing. Nothing, nothing, nothing. You'll note here, anytime I have infinite, I have nothing, because if there's no way to get there, then there's no successor to go there, right? E, D, nothing. D, E, B, D, B, and nothing. Right? This is the successor, and this is the distance. Now, how do we interpret this? I want to go from, well, let's go with A to E. I want to go from A to E. How? Right? Well, the first question you could ask yourself is, going from A to E, it's going to cost you, according to this matrix right here, 3. Now you might be able to see that immediately up here from the picture, but how do we use the successor matrix to do that, right? Computers can't look at pictures and say, yeah, here's A to B to D, or A to B, E, right? So instead we look at the successor matrix here. I asked the question, how do I go from A to E? Well, you go there by first going to B, right? So you go to B first, right? That's that entry right there. Okay, well, I go from A to B. Now the question is, how do I go to E? Well, you look it up. B to E, how do you go there? Well, you just go there, right? You just go there directly, okay? And that's what the successor matrix is here, all right? Why do we have to run it so much? Right, here's the algorithm again. Obviously, what is this going to be? This is going to be order what? Order n cubed. Right? It's not that bad when you consider that the input is a matrix, an n by n matrix. So this is not linear, but it's certainly not quadratic. Right? Remember, the input is a matrix. The input size is n squared. Call that n. Right? That's our real input size right there. So if I say that order lowercase n cubed is our runtime, well, what is that in terms of our real input size over here? N to the what? 1.5? Right? All you have to do is solve for little n here and then plug that in. Right? Solve for little n. Little n is square root of n, which is equal to big N to the 0.5. Plug that in over here. N to the 0.5 cubed is equal to n to the 1.5. That's all I was doing there. Okay? So it's not linear. It's a little bit above linear, but it's not quadratic either. It's somewhere in between. But it's polynomial. It's good. It's good enough. Right? It's certainly probably better than running Dijkstra's n times for each source. Right? Okay? The worst case scenario. The worst case scenario would be when the distance gets updated every single iteration. Right? We continually find a better and better and better path. And here's an example. An example is going to be a tournament. A to B to C. This is the exact same example I give with Floyd-Warshall's in 235 to show that you need to go the entire way. Suppose that all of these are of weight 1. Then suppose that you can go from A to C at a weight of 5. You can go from B to D at a weight of 5. And you can go from C to E at a weight of 5. Then the triples, 10, 10. And then is that it? No, then there's 1, 15. Right? This is called a tournament. It's a complete DAG. It's a complete DAG. Right? It's not a complete graph. A complete graph would have all the back edges as well. This is a directed acyclic graph, and I've put every single edge possible in this graph that I could without inducing a cycle. Right? That A goes to all of its descendants. B goes to all of its descendants, and so forth, so forth. So I've got a universal source over here, a universal sink over here. Now, why is this going to lead to the worst case running time? Remember, Floyd-Warshall's algorithm asks, well, what happens if I use A as an intermediary here? And just like on the last example, nothing will happen, because A, you can't get to A from anywhere else. So you ask the question of B. What happens when B, well, I can go ahead and go from A to E at a cost of 15, but wait a second. I can go from A to B at a cost of 1, and a cost of going from B to E at a cost of 10, so 11 is better than 15. The next iteration, you ask yourself about E. Well, I can go from A to B at a cost of 1, and then over to C at a cost of 1, so 2. And then from C, I can jump over here to E, a cost of 7. It went down again. And then you can go from A to B to C to D at a cost of 3, and then go immediately to E and find that your best cost scenario is 4. Right? So in other words, you are going to go from A to B to C to D to E, and that's what your successor matrix would look like as well. Right? At a cost of 4. This is the worst case running time. Now, you could have a little bit worse here would be if you had a cycle back on it and you didn't have a complete DAG tournament. You could go with, I don't know, 5, or just go 1 here, or 0. That'll definitely do it. Right? Say that that's free. Right? Then I can go ahead and improve E's distance as well, going from everything else. Now E magically becomes connected to everything else because it's no longer a sink. Right? I do because I want to get more practice, and together I want to develop an algorithm to actually utilize this successor matrix. So this has already been there. It is in all of its glory here, and you see that it was updated every single time, all the way down to the end. Right? I want to use this successor matrix here to understand how I can go from A to E. Right? Remember, it's a successor matrix. Right? So let's go ahead and draw it out. How do I get from A to E? Well, this entry right here tells me first you need to go to B. First, go to B. Okay, I'll go from A to B, and now my question becomes, how do I go from B to E? Well, B to E, first go to C, because that's what's in here. So A to B to C, and now my question has changed again. How do I go from C to E? How do I go from C to E? First you go to D. So A to B to C to D. And my last question is going to be, how do I go from D, this second to last line here, to E? Well, you just go to E directly. So A to B to C to D to E. And that corresponds to 1, 2, 3, 4, which corresponds to that value right there. Okay? So predecessor vertices, successor matrix vertices. Okay? What I want to do together is develop that algorithm. I think I've got it in the notes, but that's, yeah, there it is. But I like it as an exercise. All right? So as input, suppose that we're given the successor matrix. Let's check our term first. Okay, matrix S from Floyd-Warshall. Okay. Now again, if it's just transitive closure, usually I see that labeled as Warshall's algorithm. It's the same basic idea applied to minimum distance or minimum weighted distance paths. So they give a credit to both of them apparently. I don't know why. Right? The output, and also we're given 2 vertices, V sub I and V sub j. And our output is going to be the min weighted path P going from V sub I to V sub j. Okay? All right, well, I'll go ahead and initialize my path here. Where do I start? If I'm going to go from V sub I to V sub j, where do I start my path? V sub I. Right? X is going to end up being my current vertex. So that, I'll initialize that to V sub I as well. This is the current vertex. The idea that I here, my current vertex was A, and then after I answered this question, my current vertex was updated to B. So that my new question is current vertex to the ending vertex. Then it updated again and again and again until the current vertex was equal to the last vertex. So I continue while the current vertex is not equal to the last vertex. Once I'm at the last vertex, I'm done. I've built my path. Okay? Where do I go next? I need to update the current vertex. What did I do over here? I asked the question on the current vertex going over here by looking at that entry in the successor matrix. So I update it to whatever's stored in the successor matrix from the current vertex to j. Right? And you can interpret x here as being an index or whatever works for your representation. Then, as a slight abuse of notation here, hopefully you'll understand what I'm doing here, I will add x to the end of the path P. Right? If you were doing this in Python, then how would you represent a path? A list of vertices. So append, right? You're just adding it to the end. Or if it's a string or something like that. And that's it. Once I'm at the last vertex, I break out of this while loop and I'm done. I output my path P. Right? Basic idea, again, down this matrix, how do I go from A to B? All right. How do I go from X to Y? Well, you go to Z first. Okay, how do I go from Z to Y, et cetera, et cetera, et cetera, until you get to the end and you're just there. That's why when this gets initialized, look at the diagonal. How do I go from A to A? You're already there. How do I go from B to B? You're already there. This entire diagonal here is nothing more than the vertex that you're already out, that you're already at. Okay? All right. So I don't know how other or how other people structure this kind of course, but I like to take all the graph algorithms and put them together in a logical order. You'll see that this one is a great one to end on, because what we're actually doing here is a little bit of dynamic programming. There we go. What we're actually doing here is a little bit of dynamic programming. This is an optimal sub-problem kind of thing, right? What you're doing is you're asking, between two problems here, or between two potential solutions, which one is better, right? You're basically doing a divide and conquer strategy, the bottom up. And that's what we'll be covering starting tomorrow with dynamic programming. You're doing a divide and conquer strategy here because you're asking the question, how do I go from I to J? If I went to V sub k first, or through V sub k, this problem of finding a path between these two into two sub-problems. How do I find a path from this one to this one, and then from this one to this one? You've divided the question into two questions. And then you can, if it's top-down, recursion, say, okay, I'll recurse on this, recurse on this, recurse on this, until you get down to edge. Here's your solution for how do I go from A to B? Well, if there's an edge. But what we're going to do is what this algorithm did was a bottom-up solution, basically. Instead of doing recursion, it asked the question, well, what if the first one is my intermediary? What if the second one? What if the third one? What if the fourth one? What if the fifth one? Right? And the only thing that you have to be careful with dynamic programming and this kind of stuff is, can you take two sub-solutions and combine them together? And what order do you do them in? If this solution depends on this over here, then you need to compute this solution over here first. And so what we're going to end up doing is just filling out big giant tableaus, figuring out the order in which to fill them out in, and then finally which entry are we actually interested in. We're interested in this one, and then we can use this over here to build it. Right? That's what we're going to start on tomorrow, and it's our second to last one, dynamic programming, and then we'll get